In this video, we're learning about solving systems of linear equations using a method called the addition method, or sometimes called the elimination method. We'll work on problems that look like these and have answers like these. So grab a pen and paper and work along with the video. Remember, you can pause and rewind whenever you want. In this video, we're going through solving systems of linear equations by the addition or elimination method. It's called either one, addition or elimination. So here's a first example. Let's go through some background information about what it means to solve a system of linear equations. We have two equations, and we're looking for the ordered pair solution, the value of x and the value of y, that if we put them into the equation, substitute those values in place of x and y, it would make both equations true. So with this example, let's just start with x plus y equals 10. Two numbers added up equal 10. And let's make a little table, x and y. So we could say, 5 plus 5 equals 10. We could say 6 plus 4 equals 10. We could say 4 plus 6 equals 10. And that those are separate ordered pair solutions because they have different values for x and y. X is 4 with y equals, x is 6 with y equals 4 is different from x equals 4 and y equals 6. And we could make a few more examples. But what we're looking for when we solve a system of linear equations is what's the ordered pair that would make both equations true. A pair of numbers that added up would equal 10 and subtracted x minus y would equal 6. And we've got something close here with x and y 2 and 8, but 2 minus 8 would be negative 6. So if we flip that around, x equals 8 and y equals 2 would add up to 10 and have a difference of 2. So that would be our solution to that system of equations. X equals 8, y equals 2. We could write it as this ordered pair, which we understand is showing what x and y are equal to, or we could write x equals 8 and y equals 2. Now, this approach of just finding ordered pairs that seem like they could work for one equation and then checking to see what might work for the second equation is not a very efficient way to solve a system of equations, especially when we get to more realistic, more complicated equations. So we have several approaches. We can solve by graphing, we can solve by substitution, and now we have this method solve by elimination or solve by addition. And here's how it looks with this example. I'll just rewrite x plus y equals 10, and the second equation, x minus y equals 6. When we use this addition or elimination method, it's important that we have on the left side of both equations the two variable terms and written in the same order. So I have, looking vertically, the x terms lined up, then the y terms lined up, then the equal sign, and on the right side of the equation we have the constants. So with this method, we always want to have our equations in this kind of arrangement. And sometimes that can be a clue that the addition method might be a efficient way to go. If the system that we're working with starts off lined up that way, maybe we would just go ahead and try this method. So we have the alignment set up. The next thing that we'll do is we will actually do some addition. We're going to add the x terms together, the y terms together, and those constants together. It's going to look like 1x plus 1x equals 2x. Here is a key part where one of our variables will zero out. We have a positive 1y with a negative 1y, so that's 0y. We will leave that 0y out altogether. There's no need for us to add 0 to 2x. It's just equal to 2x. Let's keep the alignment going. So then we have equals, and then the right side, 10 plus 6 equals 16. Let's talk for a second about why we can do this. If you were solving an equation like x plus 8 equals 20, you would say, we see there's the variable x with 8 added to it. We should do the opposite and subtract 8. And to keep the equation balanced, we would need to subtract 8 on both sides. This is what I'm referring to, that there have been times in the past when we work with equations when we need to add some equal amount to both sides of an equation, or subtract, or multiply, or divide, and it's always legitimate as long as we're using the same quantity or equivalent quantities on both sides. So some things that you probably have not had to do so far in your life might be things like, could I add 3x plus 2 to both sides? You could. We probably haven't had a reason to do that yet, but you could. We're following that rule of the same amount on both sides of the equation to keep it a balanced, true equation. So like if we start with an equation like x plus y equals 10, I could say I might have a reason to add x to both sides, or maybe add x minus y to both sides. It's legitimate because we're adding the same amount to both sides of an equation. But instead of adding exactly x minus y to both sides, we're going to add x minus y to one side, but on the other side, we're going to use the constant, 6. Because we have this system of equations saying x minus y is equal to 6. So when we do this addition to both sides of the equation, we're still keeping it balanced because it says x minus y and 6 are equivalent. So on the variable side, we're adding the x minus y. On the constant side of the equation, we're adding the 6. And so that's what's behind the scenes, but basically we keep this alignment and we just need to add down these columns. And we're really looking for having two terms with the same variable but opposite coefficients. So when we add them together, it zeroes out. And as we do the rest of the problem, we'll show why we need that to happen. So back to our example. Now that we've had the y terms zero out and we're left with 2x equals 16, we have an equation that we can solve by isolating the variable or solving for x. We're left just with x times 2, so we will do the opposite and divide by 2, both sides of the equation. And that leads us to x equals 16 divided by 2, 8. So we have just found the x coordinate of our solution, x equals 8. We still need to find what does y equal, but we know that this solution, when x equals 8 and y equals the 2 we know, but we're about to find out that it's 2, that is the solution for both equations. When we put x into either equation, it should show us that y equals 2, because this is the solution that makes both equations true. And using this addition or elimination method is a way for us to identify first either the x or the y solution. And now that we have it, we just need to go back to either equation and see, well, now that we have our first part of the answer, x equals 8, what does that mean for y? If we look at x plus y equals 10, when x equals 8, we have 8 plus y equals 10, and solve that equation for y any way that you like, and we'll see that y equals 2. Right? Confirm what we already know, but we're showing how this method, this addition or elimination method, gets us to our solution. And if we were to use the other equation, x minus y equals 6, when x equals 8, we have 8 minus y equals 6. And we can maybe see that y equals 2 to make this equation true, or we could solve it with any of our steps that we've been using so far. There are several options that I see, but any of them, if we do things correctly on the right path, we'll get to y equals positive 2. So let's hit a few more examples where we use this addition elimination method. Here's our next example. 3x plus 2y equals 10 and negative 3x plus 4y equals 8. So we want to notice some things about this system, that it is lined up for us to use this addition elimination method where we have our x terms and y terms on the left side of the equation and the constants on the right side of the equation. And also that we have the x terms lined up vertically and the y terms lined up vertically, the equal signs, the constants. So it's really begging for us to use this method. even more, and really what's important, critical, is that we would need to check out our variables and make sure that our variable terms, at least that one, the x or the y, they have coefficients that are opposites. So I'm noticing the positive 3x and the negative 3x as a key part of doing this addition elimination method. We need to see when we do the addition, one of our two variables, at least one, zero out by having a positive added to a negative of the same absolute value. So anyways, 3x minus 3x, 0. We need that. Then with the y variables, 2y plus 4y equals 6y. 10 plus 8 equals 18. So we're making progress that we've taken two equations with two variables down to one equation with one variable. This is always going to be an equation, little asterisk, almost always going to be an equation we can solve. Basically, it will be. So we've got 6 times y equals 18. We can figure out what is y. We need to do the opposite of the times 6, do divided by 6, and then 18 divided by 6. We're left with y equals 3. There's part of our solution. So now we're actually going to go back to both as a way to check our results. We'll go back to both of these equations and see what is the solution for x when y equals 3. So the first equation is 3x plus 2y, so that's going to be 2 times 3 equals 10. We can do the 2 times 3 makes 6. Then we will solve for x. Let's take away the 6 first, work our way closer to that variable, and then we have x times 3. We'll do the opposite, divide by 3. And we have a fraction, and we'll just want to make sure that that is simplified, 4/3. So maybe I'm a little suspicious of having a fractional answer. Of course, this can happen, but let's plug into or substitute that y equals 3 into our second equation. Let's make some space over on the right side, and we're trying negative 3x plus 4y equals 8. That's our second equation. We know that y equals 3. So we have negative 3x plus 4 times 3 equals 8. The 4 times 3 we can do. Negative 3x plus 12 equals 8. Let's subtract the 12. Negative 3x equals negative 4. And finally, we will divide by that negative 3. And negative 4 divided by negative 3 does equal a positive 4/3. So we confirmed that we have x equals 4/3 as the other part of this solution, where we need to find values for x and y, values that would make both equations true, and that solution is x equals 4/3, y equals 3. Let's do another example. Now it's 4x minus 5y equals 12, and x plus 5y equals 3. Again, we've got a good alignment. 4x minus 5y equals 12, x and y, and then equals the constant. Then x plus 5y equals 3. Good alignment. And the y variables, those y terms, look good. They have opposite coefficients, negative 5, positive 5. So let's add these up. 4x plus x equals 5x. Negative 5y plus 5y is that critical zeroing out for one of our variables. And then 12 plus 3 equals 15. Let's keep going. So next we'll solve this equation. Opposite of times 5, we'll do divided by 5. And 15 divided by 5, we've got x equals 3. First part of our solution. Now let's find the value for y. If we go to our first equation, 4x minus 5y equals 12. When x equals 3, we have 4 times 3 minus 5y equals 12. Takes us to 12 minus 5y equals 12. Let's keep going, try to isolate that variable y. We can subtract 12 from both sides of the equation. And let's just be cautious with what we see here. On the left side, 12 minus 12 zeroes out. That was our goal. But on the right side, we have, again, 12 minus 12. That will just leave us with 0. It's not, we don't have a crash and burn of anything. It's just stay the course. It's just saying that this value of negative 5y, it must equal 0. You've got 12 minus something unknown, 5y, but this 12 minus unknown equals 12, then that unknown, the minus 5y, has to equal 0, because if you take away nothing, that's how you stay where you're at. 12 minus 0 is 12. So, in the future, we'll see some things that are a little more problematic or need extra interpretation, but stuff like this, just be cautious, and we're still solving an equation. It's just going to tell us that if negative 5 times y equals 0, then therefore y has to be 0. The only way you can multiply things together and get a result of 0 is if you started with a 0. So negative 5 times 0 is the only way that you can say negative 5 times y equals 0. So there's our solution. X equals 3 and y equals 0. But let's go ahead and check in the other equation just to get a little more confirmation. X plus 5y equals 3. We started off finding that x equals 3. So we're looking at 3 plus 5y equals 3. Again, we're seeing something familiar here. 3 plus something equals 3. So that 5y, again, must equal 0. And if 5 times y equals 0, that means that y must be 0. So we've confirmed it. The solution is x equals 3, y equals 0. Now here's one for you to try. So pause the video and try this one out. Remember how we've approached these problems. We've been looking to make sure they're lined up correctly. We've been checking to see if one of our variables will have terms with opposite coefficients that when we add them together, they will zero out, leaving us with an equation, one equation with one variable, which we can solve. And then we have to check that equation, that solution back into one of our original equations to find the solution for the other variable. So do all those things, pause the video, try it out, and then when you're ready, restart, and we'll look at the answer together. Here's the solution I found. X equals positive 3, y equals negative 1/2. So I liked the alignment of the equations. I found that the y terms will zero out, negative 4y with positive 4y. The additions, 3x plus 5x equals 8x. For the constants, 11 plus 13 equals 24. Solving for x, we divided by 8 both sides. Here's where I am right now. And that led us to our first solution, x equals 3. So there was just my original work based on having nice setup for our two equations. Once we've got x equals 3, I first checked it into that first equation and got 9 when I do 3x, 3 times 3 equals 9, minus 4y equals 11. Solving that, subtract 9, and then dividing by negative 4 took me to a fraction, y equals negative 1/2. Then I did a check on the other equation, 5x plus 4y equals 13. And 5 times x when x equals 3 makes 15. Subtracted 15 and then divided by 4. Confirmed that y equals negative 1/2. So there's our solution written as an ordered pair. So now let's go on to another example or two where we don't have a very good setup to start off our problem. Let's talk about how we need to make some adjustments to get it into a good place for us to use this addition elimination method. And then we'll look at an example or two of some different kinds of outcomes when we can't actually get an ordered pair solution for our system of linear equations. Here's our next system of linear equations. This time, we should notice that we don't have that good alignment. We don't have both variable terms on one side of the equation with constants on the other side. So our first equation doesn't have that form of like an ax plus by equals c kind of form of an equation. So we just need to do some rearranging up front. We do prefer to have things with that kind of setup, so we'll keep that second equation the same, 2x minus 3y equals 15. But we'll do some work with the first equation. 3y equals 4x minus 9. And if you've been working on solving systems of linear equations by substitution recently, you might have some ideas about using substitution when you have one equation where a variable is solved, or at least partially solved, like this one where it just has a times 3. You might think, could I go take this to a substitution method? And you could. Really, all of these problems about systems, there are pros and cons for the different processes that we use, but they would all get us to that same solution, whether we solve by elimination, addition, or substitution, or graphing. So there are different tools that we have for solving these systems. So we will focus this time on addition, elimination. We want to notice that 4x term is not in the place where we want it. We want it over on that left side with the 3y. So again, we just do things like same quantity to both sides of an equation to keep it balanced, and that helps us to zero it out from one side and kind of move it to the other side. So the 4x, we don't like it where it is. We want to completely move it, which means we will subtract 4x, that entire term, from both sides of the equation. So that zeroes it out from the right side. We are left with negative 9 on that right side and no other variable terms. So we're making progress. We've got x and y both on the left side. And let's make sure that we write it with the x term first and that we are very cautious about our signs. So that 4x is really a negative 4x. It was subtracted from both sides, so that makes it negative 4x. And the 3y was positive, so negative 4x plus 3y. So we had a little rearranging that we had to do, but now we are in a good spot. Let's just make sure I'm copying things over correctly. Those y terms are looking good with their opposite coefficients, so we're ready to add. 2x plus negative 4x would make a negative 2x. The negative 3y and positive 3y zero out. That's a critical part. And then 15 plus negative 9 equals 6. Great, we're down to one equation with one variable. Let's divide by negative 2 so that we can solve for x. And we see x equals negative 3. Let's just wrap up as usual. We want to actually, I suggest that we go all the way back to our original equations, even the one before we rearranged it to get that good alignment. It's just always best, I think, to check with the original problem so that if we made a mistake anywhere in our work, we'll be able to detect it, hopefully, at this point. So it's tempting to just, should I plug back into where I had them here? And I would say, no, go all the way back to the beginning to plug in, to substitute. So we had 3y equals 4x minus 9. We'll do 4 times negative 3 minus 9. That's 3y equals negative 12 minus 9. 3y equals negative 21. And then we divide by 3, and we've got y equals negative 7. Let's check it with the other equation. 2x minus 3y equals 15. With x equals negative 3, we've got 2 times negative 3 minus 3y equals 15. And let's just keep it going. Now we're going to solve for y. Let's get rid of or zero out that negative 6 with a add 6 to both sides of the equation. Be cautious with what we have left over when the 6 and the negative 6 zero out. We still have a negative 3y, and on the right side it equals 21. We'll divide by the negative 3, and we get to the same result. Y equals negative 7. So we have our solution to this system. X equals negative 3, y equals negative 7. So now let's look at another style of system that comes to us that is not ready for this addition elimination procedure, and we'll see what kind of adjustments we need to make, and then we'll see how the problems wrap up in this familiar kind of a way. Looking at this example, we see that it has the good alignment of x terms with y terms and then equals with constants on the other side, but we don't have this critical piece of having variable terms that have opposite coefficients, so that when we add them together, we will see that variable zero out. If we tried to add the equations together right now, we would see 5x plus negative 3x equals 2x, and 2y plus y equals 3y. And then on the right side, 14 plus negative 15 equals negative 1. We would have we'd have one equation with two variables, which we cannot solve and get a number answer for one of those variables. We really think about these approaches as being able to go from two equations with two variables down to one equation with one variable, which we can solve. So that is not ready for us to, I mean, we can add, it's valid, but we didn't eliminate. So we, thinking about addition elimination method, we want to eliminate one of those variables. So we have some extra upfront steps that we have to do, and then we'll see the problem play out like the ones that we've been working on so far. We will also be using an LCM, a least common multiple, as part of this step. So what we need to do is first decide which variable do we want to try to eliminate. Let's start with the x's, then we'll do it with the y's so we can see how it all plays out. If I was working on this problem by myself, I still might choose the x's because currently one is a positive number and one is a negative. So they're different signs. We would just need to get them to have the same number part. Like could it be a positive 5 and a negative 5, or a positive 3 and a negative 3? And as it turns out, it's really the common multiple that we want to use. We want to get them to be a positive 15 and a negative 15. We will have a lot of thoughts similar to thoughts that you might have if you had to add or subtract fractions that had denominators of 3 and 15. We might be thinking about things like, okay, I need to build up those denominators from 3 and 5 into a common denominator, which is the common multiple. Maybe you did that by making lists of the multiples to see which multiple is on both lists, and also try to find the lowest one, just to keep your work to as small numbers as possible. And that could be a way that we see that 15 is a common multiple and the least common multiple. And once we have chosen 15, then we would have to do some multiplying. We would go and say that denominator of 3 needs to be multiplied by 5. And if we're doing it there, we have to do times 5 up in the numerator to keep everything legitimate, not changing any quantities. With the 1/5, we would need to multiply by 3. If we do it to the denominator, we have to do it to the numerator. We're going to have very similar thoughts as we find a common multiple and get our x coefficients to be that common multiple. So maybe I'll just leave that right there for now. And maybe we would still do this list to find the common multiple 15. And we've also done it with prime factors as a way to find common multiples. So let's not focus too much on how to do the common multiple. Let's just say we know how to do common multiples. How do we use them in these problems? We do some, again, it's about multiplying. So let me just rewrite the first equation, 5x. Let me do a little more space. 5x plus 2y equals 14. We'll also rewrite the bottom negative 3x plus y equals negative 15. And the way that we multiply to get the new LCM, that common multiple, is that we have to multiply this number to both sides of an equation. That's our way of keeping things legitimate. You can add, subtract, multiply, divide, do whatever kinds of operations as long as it's the same quantity to both sides. So the top equation that has a coefficient of 5 with the x needs times 3 to get that up to a coefficient of 15. I'm just going to write it horizontally here. I've noticed what I did here. I put parentheses over the entire equation, which is kind of a weird thing to do, but it was my shorthand of saying I need to make sure I multiply this 3 to every term that we see. Let's write it in a little bit of a more responsible way, I think. And so let's say it's this side, all the terms on the left side need times 3, and all the terms, which is just 14 on the right side, need a times 3. Okay, I like that a little bit better. So let's distribute. 3 times 5x makes 15x. 3 times 2y makes 6y. And then equals, on the right side, 14 times 3 is 42. Let's keep that stuff over there. Now, for our second equation, which has a coefficient of -3, we need to do that times 5 to get that common multiple of 15. And in fact, the opposite, -15, because that's really what we need for the addition part to do the elimination. So 5 times the two terms on the left side, -15x plus 5y. And on the right side, -15 times 5 is -75. Great. Okay, that was a little bit of upfront work, but it got us to a system that is something we're hopefully familiar with. We see the good alignment. We see the x terms have opposite coefficients, and we've done a few problems just like these, and so that's how this one is going to play out. Let's take care of stuff, but it's going to be pretty familiar, hopefully. 15x plus -15x zeroes out. 6y plus 5y is 11y. And on the right side, 42 plus -75 is -33. Great. One equation, one variable. That's a good thing. We can proceed from here. Let's finish solving for y. Divide by 11. And so we've got -33 divided by 11 is -3. There's our solution for y. Remember, we need to find solutions for both variables, and we wrap up these problems by finding one solution and then going and substituting back into our equations to find the other. Let's do that. Our top equation, 5x plus 2y, now is 2 times -3 equals 14. 5x plus -6 equals 14. And let's just keep rolling. Solving for x, we'll add 6. We're looking at 5x equals 20. I like working with whole numbers here. Dividing by 5, we've got x equals 4. Let's go ahead and check in the other equation just to be certain. -3x, let's squeeze it in right here. I feel like squeezing stuff over. -3x. Remember, we're still checking our first solution here, y equals -3. Going all the way back to our original equations, -3x plus y means -3x plus -3 equals -15. Let's solve for x. Adding 3 on both sides now gets us to -3x equals -12. And then dividing by -3 shows x equals +4. So confirmed, we have an ordered pair solution, x equals 4 and y equals -3. Now, at first, I promised that we could do it by eliminating the y variables also. So let's stick with this problem. Let's see what happens with the y variables, and then we'll come up with an example for you to try. So we've cleared everything out aside from our solution that we just found, x equals +4, y equals -3, because we want to make sure that whatever process we choose, that we always get to that same result. So we also want to illustrate that when we have to make some adjustments to get the coefficients to be opposites, that we have to get them up to be a common multiple, that we can do that. We can choose either variable to eliminate. We just saw how it played out with the x variables, the x terms, and let's see how it plays out with the y terms. I'll start off just by recopying the two equations. Our y coefficients are a +2 and a +1. And if you thought about what if these were denominators, how would I get a common denominator? Well, when one of your denominators is 1, it's pretty easy to just use the other number as the common denominator. Keep the 2 as a 2 and just do the 1 times 2. And if you multiply the denominator by 2, you have to do the numerator times 2 to keep things legitimate. So a similar kind of idea. Our common multiple would be 2. And our first equation really doesn't need any change. But our second equation needs multiply by 2. It looks like, but maybe you're noticing something about that multiply by 2. So no change to the first equation. I'm just going to write like times 1 to sort of say, yeah, I'm really trying to show that I'm changing things to multiply, but I don't want this to change, so let's just call it I'm multiplying by 1. Now, the bottom equation, we have a 1y. We need to multiply by 2 to get to that common multiple. But if we just multiply by 2, I know I'm doing some shorthand, but we're going to back up and do this properly real quick. If I just multiply by positive 2, and I did that to all the terms in the equation, we have the y terms with the same coefficient, that common multiple 2, but they're not opposites. So that's another thing that we have to keep in mind when we do this multiplication. We would look at that second equation, given that the top one is staying the same, and we would say, yes, we need to multiply it by 2, but if we do that, our y terms will not be opposites. So we really need to be multiplying by negative 2. So to the left side of the equation, I'll put it in parentheses, multiplied by negative 2. To the constant, we need to multiply that by negative 2 also. And let's see how this transforms our equation. Negative 2 times negative 3x would be a positive 6x. Negative 2 times positive 1y would be a negative 2y. And if our goal was to eliminate those y terms, looks like we do have ourselves set up to do that. But let's avoid what is maybe one of the most common mistakes to make through these problems, is to kind of forget about the constant. Also needs multiply by negative 2 to get us up to a positive 30. Okay, so that's the change that we would have needed to make if we are eliminating the y terms, the y variable terms. But now that we have them as opposite coefficients for those y terms, we're ready to proceed as usual. 5x plus 6x, 11x. 2y negative 2y, 0 out. 14 plus 30 is 44. So we're looking good. We're down to one equation, one variable. Let's finish solving. Divide both by 11. We've got x equals positive 4. Looking good. That does confirm what we found earlier. Let's do a quick, not quick, let's do what we need to do, which is, what does y equal? We've got the x. Let's not go too fast. I got a little excited, thought I was done. Not yet. So 5x, that's going to be, if x is 4, 5 times 4 plus 2y equals 14. So that's 20 plus 2y equals 14. We'll finish solving for y, so we subtract 20. We've got 2y equals negative 6, and then divide by 2. We've got y equals negative 3. Solution confirmed, but we do like to check that in both equations, so let's do that. The second equation, negative 3x, is going to be negative 3 times 4 plus y equals negative 15. So that's negative 12 plus y equals negative 15. Added 12 on each side to zero out that negative 12. And again, we're seeing y equals negative 3. So that's how it's going to play out if we choose to eliminate the y terms. And I can see an advantage there. I thought there was an advantage with the x's, that they started out as different signs, one positive, one negative. So I thought that was kind of a help. Some people might look at the y variables and say, well, there's a way where you can not touch the first equation and only transform that second equation. And that's a nice path. So we've got options. They take us to the same solutions. Now let's bring up an example for you to try, where you will probably have to do some transforming of those equations to get the coefficients to be opposites. So you're going to go through the whole process. So let's bring up an example for you to try. So pause the video to try out this problem, and when you are ready, restart the video and we'll go through the answer together. For this system of equations, neither variable really stood out to me as an efficient choice to eliminate, neither the x nor the y. So let's take a look at how it would play out with both options. So we'll start by eliminating the x, and we'll follow up by eliminating the y to see how both ways look and make sure that we get the same result. To eliminate the x terms, I'll choose to multiply the top equation by negative 4 and the bottom equation by positive 3, so that both coefficients will be 12, but opposites. The top one negative 12, the bottom positive 12. Understand that if I multiplied the top one by positive 4 and the bottom one by negative 3, it would still work out just fine. I do want to make sure that I don't forget about multiplying the right side, those constants, by the same factor that we use on the left side to get the common multiple. That took me to these two new equations, negative 12x plus 28y equals negative 56, and positive 12x minus 6y equals negative 54. And if you had used a positive 4 with a negative 3, you will see some similar coefficients, but they'll be opposites. They should, I think, essentially all of them be opposite of what I currently have here. And when we add to eliminate those x's, I think that we should end up with either the same equation right here, or more clearly for us to see that we have opposites. So you might have a negative 22y equals positive 110. Whereas at this point, once we get to the solution for y, we've all got the same thing. If we don't all have, let's make sure, negative 110 divided by 22 is negative 5. We all need to have y equals negative 5. Doesn't matter if we've taken different approaches. We need to have that same result at this point. If we don't, there's a place somewhere where we've gone off path. We made a mistake. So I'm pretty confident. I actually did this problem a few times already. So I think y equals negative 5 does sound accurate. So that's only halfway there. We still need to figure out x. So let's substitute into these equations. Into the top one, 3x minus 7 times negative 5. And let's just play this whole thing out. So I've got 3x plus 35 equals 14. Subtracting 35 got me to 3x equals negative 21. Dividing by 3, I've got x equals negative 7. Let's check the other equation. 4x minus 2 times negative 5 equals negative 18. That becomes 4x plus 10 because we've got negative 2 times negative 5. That equals negative 18. Solving for x, so subtract 10, we've got 4x equals negative 28. And then dividing by 4, we've got x equals negative 7. So we've got our solution. X equals negative 7, y equals negative 5. Let's take a quick look at doing this same problem, but eliminating the y terms and make sure that we get to the same result. And if you had already tried this problem once with the x terms and it didn't quite go so smoothly, then let's retry it with the y terms. So pause the video, try it with eliminating the y terms, and when you're ready, restart the video and we'll look at that solution together. To start off, I rewrote the two equations, and to zero out the y terms, I decided I needed a coefficient of 14. And so I multiply the top equation by negative 2 to make that a positive 14y. And I'll multiply the bottom equation by 7 to get that to be a negative 14y. That's where I'm hoping to see those opposite coefficients. Doing those multiplications took me to negative 6x plus 14y equals negative 28. And for the bottom equation, 28x minus 14y equals negative 126. The y terms look good, being opposite coefficients, that those will zero out. We're looking at 22x equals some big addition going on right here, negative 154. And then when we divide by 22, you learn something new every day. 154 divided by 22 equals 7. So this result is a negative 7. That confirms what we were hoping to see for our solution for x. Okay, so we had some large numbers involved there, but same result. So that's good. Now let's find our solution for y. We found earlier it was negative 5, so we've got a goal in mind. 3x, looking at that top equation, now is 3 times negative 7 minus 7y equals 14. And let's solve for y, and that does work. 3 times negative 7 is negative 21, and then I add that to zero out the negative 21. On the right side, 14 plus 21 got us to 35. And then dividing by negative 7 gives us y equals -5. Let's check, just to be thorough, into that other equation, 4x. That's going to be 4 times -7 minus 2y equals -18. And it did check out. 4 times -7 made -28. So then I added 28 to both sides to get -2y equals a +10. And dividing by -2 gives y equals -5. So we have got the same solution. X equals -7, y equals -5. Now let's look at two last quick examples, because hopefully you remember from solving systems by graphing that when we look at the graph of the two lines, the solution is that point where the two lines intersect. And based on the equations that we have, we might have two parallel lines that never intersect. So we have systems that can have no solution. We also, maybe I'll have to look at some real graphs instead of just my hands. We also can have two equations that when you graph them, it turns out that they're the same line. So in terms of what points are on both lines, every point that's on one line is also on the other line. So it's like you find a solution for one equation, you've automatically found what works for both, but there's not just one that works. There's an unlimited supply of them that work. So ideas that hopefully you've seen with solving systems by graphing, and also hopefully investigated when you solve by substitution. Let's just look at how it plays out when we use the addition or elimination method. Let's take this system for an example. And we notice that we have good alignment, but we don't have opposite coefficients for the x's or for the y's. So we can't add them up right away. We need to do some multiplying to get a common multiple in our coefficients. So let's choose to eliminate the x variables. What we see is going to play out if we choose to eliminate the y variables. So to keep things a little to the point, more to the point, we will just be eliminating the x variables. With those coefficients being a +2 and a +4, I think we can have a common multiple that is a 4. So we will not do anything to change or transform that bottom equation. We'll keep it as is, but we'll multiply the top equation by a -2 so that we can make our coefficient on the x be a -4 and be ready to eliminate, zero out when we add those equations together. So no change to the +4x, but to this top equation we'll multiply by -2 because that gives us for our x term a -4x. But as we continue to do the distribute, we notice that it also produces a +10y, and then 9 times, that should be a -2, let's be careful, equals -18. So we have opposites for the x coefficients, but we also have opposites for the y coefficients. And let's see what happens when we add these equations together. We eliminate the x's as well as the y's. What that really means is that on that left side of the equation, we have left 0. So left side, we've got the number 0. Right side, we have -18 plus -12 equals -30. That's what's left. We've done all of our steps. We'll just do a quick double check. I almost went off path right there with the 2, -2. So let's just do a quick look again. Did I recopy the equations correctly? 2x minus 5y equals 9. 4x minus 10y equals -12. Okay. I did the top equation times -2, so that took us to a -4x, +10y, and the constant is a -18. And then when we add the x terms and the y terms, definitely zero out, and then we're looking at -30 on the right side. So all of our math steps are correct. It's telling us that this system can never have a solution because 0 can never equal -30. It says the x's and y's have both zeroed out because it doesn't even matter what numbers you use for x and y. You can never find one ordered pair that's going to work for both. So this tells us there's no solution. What was the case when it came to graphing for us to have no solution. Okay, I'm not going to do my hands. Let's look at an actual graph. And hey, the equation's already made. So let's look at graphs of those two equations. And hopefully we're going to see parallel lines. Because if there's no solution, there's no crossing of lines. How can there be no crossing of lines? Only one way, that they are parallel lines. However they're pointed, they're parallel. They never cross. They make no solution. Okay, here's Desmos, a wonderful tool for all sorts of things, but for making quick graphs for your video is a great thing that it does. So I put in the two equations. The graph of the first one, 2x minus 5y equals 9, is right there. Graph of the second equation, 4x minus 10y equals negative 12, is right there. Do those lines ever cross? They seem to be totally parallel. And if you were to find the slope of those two equations, which you can do at this point in your life, if you're studying this stuff, you should be able to take equations and find slopes. You'd be able to show that they have the same slope. So they are parallel lines that will never cross. Therefore, we have no solution. So let's look at one more example that you might remember from substitution or graphing, or from what I said just a few minutes ago. It's possible to have two equations that are actually the same line, where we would have an infinite number of solutions. Here's our system. We've got good alignment, x's, y's, equals, constants. Nothing is set up to be eliminated. No opposite coefficients. So again, what we see that is going to happen with the x terms would happen with the y terms. So we won't do both. We'll just go right for the x terms. And we'll recopy, and it looks like a common multiple for 4 and 10 would be 20. So that's going to be our target coefficient for the x terms, 20. And as usual, one positive, one negative, so that they'll be eliminated. I've got myself set up to do the top equation times 5 to get a positive 20x up there. The bottom equation times a negative 2 to make the negative 20x. That does give us opposite coefficients for the x terms. It does again give us opposite coefficients for the y terms, but it also gave us opposites for the constants. So when we add those equations together, the x terms zero out, the y terms zero out, everything on the left side zeroes out. That itself is not anything that leads to a conclusion yet. It's only when we see what is the statement, what's the equation that's left behind. Before it was a nonsense, like 0 equals 30 or negative 30, whatever it was. It was like, this can't ever be true. That's what we're investigating. What statement is left behind? And in this case, when we do 60 plus negative 60 equals 0, we're left with a true statement. 0 equals 0. This is telling us that because the x variable and the y variables zeroed out, both of them, that the result has nothing to do with those actual values. X and y could be anything. You'll always end up with a true statement. So as long as x and y works for one, it's going to work for the other, is really the conclusion we should make. So I think somewhere in there I said a sentence that sounded like any number, any pair of numbers would work. That's not what I want to say. I want to say if it works for one equation, it's guaranteed to work for the other equation, and that it's actually telling us that we have the same equation. And there are different terms that could be used. People might say that in terms of this system, it is a dependent system, that your solutions for the system, for what works for both equations, it really just depends on what works for one equation. If you find something that works for one, it's going to work for the other. What does that mean in terms of the lines? If it works for this, it's guaranteed to work for the other line. They must actually be the same line. So let's do a quick Desmos check and confirm that. I've got both equations typed in. Let's first look at the graph for 4x plus 6y equals 12. There it is. And our graph for the second equation is right on top of it. It is the same equation. They make the same line. And if you were to apply some past skills about linear equations, you could identify that they have the same slope, but also the same intercept. And that really tells us that they are the same line. The last equation they had, or the last problem that we looked at, they had the same slope. They were parallel, but they wouldn't have had the same intercept. That tells us they're parallel but different. Here, a same slope says, again, they're parallel, but they'd have the same intercept also to say they're actually the exact same line. So those are those two extra outcomes that we might see. Frequently, we'll probably see a system that we can take to a single ordered pair solution. The one point that is the solution to both equations, that if you graphed those two equations, they'd be two separate lines that cross at one point. But we have these two other cases, like your equations in a system might actually be parallel lines that have no solution, or they might be actually equivalent equations, that they're actually the same solution, with the same equation with the same graph, and so they have infinite solutions. Whatever solution works for one, it's going to work for the other. They will not have just one point where they intersect. They will not have just one solution. Make sure you take time to practice these problems. They're a little bit lengthy, they can have a lot of steps, but they're totally doable, and it takes you doing them to get good at them. So good luck and stay tuned.